Okay, and we began with this outline. I did define focal point. I have to say I didn't define focus very well. We showed that if you have curvy surfaces, they can bend light either as mirrors or as lenses. The difference being that in a mirror, you're using the reflection from the surface, and if the surface is curvy, you can get focusing of the light. And if on the other hand you use solid materials like these lucite lenses. Let's see, do I have my arrow here? No, I guess. Oh yeah, maybe so. Yeah. Pen. Okay. Okay. Maybe I have something. Anyhow, if you have these shapes, what you get in the case of lenses is light coming in, and it refracts at each of the surfaces as it goes in and as it goes out, and you can bend the light and achieve these interesting things. Now, the other point that I made is I did define, I thought pretty well, the focal point. And that is, the focal point is if you have one of these, let's say we're dealing with mirrors. Okay, we'll do both. Okay, you have a mirror like this. This is our standard configuration for a mirror. It's cut from a sphere, so it's a spherical surface, and it's metallized on one surface or the other. Could be this surface too. And the light that travels parallel to the axis of this mirror is reflected because this is a circle. It has a radius to this point and is a perpendicular here to the surface. So the light comes in at a certain angle and reflects by the law of reflection this way, and passes through the axis at a point that we call the focal point, and the distance from the mirror is called the focal length. Now, the point I did not make clear was that we're going to be talking about images where the light is focused, and you have to make a distinction between the focal point and where the image gets focused. The focal point is only the place where the light comes through. It's a very useful point, and it appears in the formula. But where an image forms is an entirely different matter. In a case like this, for example, we have different rays that we know are simple. One of them is the one I drew here, the one parallel to the axis, and it reflects, and it keeps going like that. But we can also have another ray, for example, one that passes through the focal point, again, and because it passes through the focal point, it reflects parallel. So it's an imitation of this one. The one that runs parallel reflects and passes through the focal point. This one that passed through the focal point on the way in will reflect back parallel. So that, where those two rays intersect, this one and this one, that is the place where the light has come back together, and that is the place of the image. Get another color here, perhaps. That's the image, and you'll notice the image is we say the light has focused, but you see it's not at the focal point. We're getting an image. That one point from there was imaged here. So it's focused at this point. So that's, in a way you could say that's the focus, but it's not the focal point. Or the focal point only serves as the place through which the light will pass on its way to doing something useful. So do make a distinction between those two things. question on that? Think about it. Yes, sir.
Would you mind repeating how you knew that exactly was the focus?
How I got that focus?
Yeah.
Yeah. I'm trying to find two rays that I know are simple. And there are several rays that are simple. I have a later slide here that perhaps goes in. This one here, if you can. Is that clear? There are several rays, this is a mirror, that are simple. Here's my mirror, and let me call that the center of the mirror. And it was sort of a blown glass sphere, and I metallized the inside. So I have the center. It turns out the focal point is halfway. It's the radius over 2. In other words, if I blew a bubble of radius r, it turns out we proved that last time. You can look at it in the notes or in the book. Very simple proof that the focal length is half the radius. Did I do it halfway? No. This is more like half. Okay. Now, so there are some special rays. One of them is one that goes parallel to the axis, and we can show geometrically that the reflected ray will pass the axis through that point. Agree with that one? Okay. Now, let's say, so here's where the light is coming from. And another ray is passing, that's the one I drew in yellow, passing through the focal point. Now, can we show that that is going to go parallel? Let's see. I drew another radius here, radius of the circle, right? And because that's a perpendicular, I have the angle of incidence here, and I have the angle of reflection here equal. Okay? Now, look at the geometry here. You agree this was parallel to the axis? Now the question is this parallel to the axis? Now, let's see. All I have to prove is that this angle is equal to this angle, and those are interior angles or parallel lines. Remember that from geometry? So it will turn out that if, let's see. Yeah, I mean, you can see that this height here is going to be the same as this. Can we see that? Is that obvious? We have an angle here. I'm not sure if it's so obvious, but it is true, at any rate, that this angle is equal to this angle. And so if this ray was parallel, this will come out parallel as well. Let me not stop to try to figure out how to prove that, but I think it's going to be true by the geometry. So these are two rays that are easy to deal with. One, where it starts out parallel and reflects through the focal point, not the focus. And the one that goes through the focal point will end up going parallel. Now, another simple ray is one that goes and hits the mirror here, and again, by the law of reflection, will reflect back out at the same angle. That's another one. And the fact is that that ray should also intersect at the same point here. They all recombine at the focus. So this is the focus of those rays, and will create an image over here. The image is created at the focus. Okay, so those are three good rays. Do I have a fourth? those are three. Let's see, a ray that reflects from the mirror after passing. Oh, if it passes through the center of curvature, that's another one. Yeah. So in other words, if I should have a ray that went like this, right through the center of curvature, it's going on a radius, and so it'll bounce straight back. So that's yet a fourth one. This good? So if I had a ray that went this way and struck the mirror here, it's striking it at right angles, so it's going to bounce straight back. And again, it will pass through that point. It'll pass through the focus. Yes?
So are you saying that if we have different special rays, the point at which the reflection crosses?
That's right. Because that's, that goes back to our nice demo that the way this thing is working is that if you have some kind of an object, which we keep drawing arrows just to keep it simple, the light is going out in every which direction, and it's unfocused. If you want to get an image, that, for example, on your retina, or to project an image on the screen like you see here, the light has to somehow be converged and brought to that point. And whatever ray, a lot of rays go out, but some of them miss the mirror altogether. Most of them hit it at some kind of a hard angle, which is very hard to figure out what it's going to do. But there are some, these four, that it's easy to figure out what it's going to do. And we just take for granted that all of them, even the ones hard to figure out, they'll also pass through the focus. But at least those four do. So we can verify that at least all you really need is two. When two of them intersect, that's where the new image is. If you go through and you check the other two, you get all four rays that are easy, you will see that they all pass through that point. So it's all recombined there. So we just use that for simplicity. But all the rays that the mirror catches, all of them, will go through this focus. But the ones that are easy to do are those that are, through the focal point, boom, 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 that you can follow. It's just to make life easy. Okay, so that's very, very good point that you made. And let me see. Okay, so the point I wanted to make very clearly is that you have the focal point, which is a useful tool for getting the where the light will go and how it will pass and form an image at the focus, if there is a focus. And we have these different things, and I did give you rules that if the mirror and the lens are in this standard form that I defined here, my definition, it's not a standard in the books. I don't think you'll find this anywhere. But if they're in the standard form, all these quantities are positive. If any of them differ from that standard form, we give it a negative sign in order for the formulas to work. And we'll see, I'll give you an example here pretty soon, on how to use the formulas and get when it's negative, when it's positive, and so on. But so the standard form is a concave mirror, an object outside the mirror. It's pretty hard to have the object inside the mirror, but that could happen actually. If a second element is projecting an image behind the mirror, it's conceivable that the object could be behind the mirror, but if it's in front, it's positive, and if the image is in front, it's positive. Likewise, the standard form that I define is where you have a converging lens meaning one that's fatter in the middle than on the outside. This is a converging lens. This will make light that's parallel, it'll make it converge. As compared to a lens like that's skinny in the middle, and that's the kind of, or thinner in the middle than it is on the outside, could actually be something like this as well. But as long as it's skinnier in the middle than it is on the top, it's a diverging lens. Light coming in parallel will diverge for something like that. So that's a converging, and this would be a diverging lens. Okay? So the standard form that I'm defining is that Oh, look how that is cut off the thing. So that should say lens. And it's got the PowerPoint's a little distorted. So that's a lens. It's a converging lens. And if the object is on one side and the image is on the other, that's standard. If it should happen and it can happen, that the image is on the same side as the object, then we would call that image a negative image. So I find that an easy way to remember whether to give a plus or minus sign to the formula. And that is, as I said, the same formula applies to both lenses and mirrors. You just have to know what you're dealing with. Then we have this point here. I think I'll get to the spherical lens story. The fact that the focal point is half as long as the radius is easy to prove. The lens maker's formula is harder to prove and a little bit harder to use because you have two surfaces in a lens. And you have to deal with the radii of both surfaces. Because, for example, a case like this, the radii are different. But that formula takes that into account. And I think I'll have time to go through the details of that. And let's see, is there anything more to say about this? Oh, yeah, this note at the bottom, this is something I try to say. The fact that if the radius is smaller, the focal length is shorter. You can sort of see that because, as I say, here's my motto, flat does not focus. If you have something that's flat, it won't focus things. It'll reflect them straight back. It doesn't converge the light nor diverge it. So a thing is flat. Also, if a lens is flat, then like that would be plate glass. What happens is the light refracts this way, and then when it comes out, it refracts that way. So basically, it's coming through straight. It doesn't converge the light nor diverge it. So in the middle of a lens, that's why we draw this line through the lens as a straight line, because basically it's just shifted a little bit, but that doesn't converge the light. Whereas up here, you have more or less of a triangular shape. Light coming in this direction will bend toward the normal, and then over here is going to bend away, and so it'll converge the light. Likewise here, it'll converge the light. But flat surfaces don't focus anything. So that's another little motto. And the smaller the radius, if you have so you go from one way of looking at it, let me see if I have a better picture here for you. Okay, well, I will. And here, as far as magnification, the further the thing is away from the lens or the mirror, the larger it is. So if your image is further away, it'll be further away than the object, then it'll be larger than the object. There's another quick motto you could have. The further away it is, the larger it is. If you work out a formula and it doesn't come out that way, you made a mistake somewhere. So if a thing is close, it'll be small compared to if a thing is far. Because as the image grows, the further away you get, the image grows. So that's another motto, quick test. The more distant it is from the larger. So if one is close, it'll tend to be smaller than the one that's further, whichever way you look at it. So that's the magnification story. And we define if the image and the object are pointing in the same direction, they will have the same sign. If they happen to point in the opposite direction, like this one happens to, then we give the height here one sign, we give the other one the negative of that. Typically, if it's above the axis, we say it's plus, and if it's below the axis, we'll say it's minus. That's to tell you whether it's inverted or upright, which is good to know. Then here are those special rays that I talked about. I hope you've got them. And likewise, we'll find when we get to lenses, and hopefully quickly, that you have special rays for lenses too, which make life easy. The light going through a lens will focus at a certain place. All the rays from a certain point will go to the corresponding point in the image, but the special rays are the ones that are easy to follow. And they're the ones which will help you define where the new image is created. Okay, so we proved that. And we have the standard form shown here. Things are in front and of a concave mirror, and they're all positive. But if you have if, for example, in this case here, this is not entirely a bad thing to talk about. Actually, this particular situation is familiar. The one I drew there, I had see, funny things happen as you pass if here's the center of the circle and here's the focal point of a mirror. Well, let's just follow qualitatively what's happening. The formulas will tell you the same thing. Here, if you're outside the center, your image will form, pass through here, you reflect through here, your image is going to form here. That's where those two rays cross. Can you see that? Okay. Okay, so notice that various rules that I said are in place. Because this one is further from this one, it's larger. So actually there's a reduction in size. So the rule, the further you are, the taller you are, is working. Okay, now where this changes is when you get to the center of the circle, and here's your focal point. Here's my ray 1. Here's my ray 2 going through the focal point. What you'll find is that when you're at twice the focal point, at 2f, or at r, your object and your image are of equal size. They're just upside down. In other words, putting it in the formula, 1 over s, 1 over s prime or plus 1 over s is equal to 1 over f. When you are at, let's say your s is at 2f, so you get 1 over where the image will be. Let me put, so is plus s is equal to 2f equals 1 over f. So 1 over s prime is equal to 1 over f minus 1 over 2f. So it's 1 over f minus a half f, which is 1 over 2f. So s prime is at 2f. So they're and that's where s is. So at that point, they are equal in size, and they're equally distant. So it follows the rule. Your size depends on how far you're from the lens. He was further away, this guy was shorter. And it depends really on where you are with respect to the center. At the center, you're equal. And if the object, let me color code them a little bit. If here's the object, if you go further in, you will, if here is your center and here is f, if you're in here, it will turn out that the image is further away and will be larger because he's further away. You can do the arithmetic. And things go along pretty well until you reach the focal point. And then the very interesting thing happens. the now, if you do your construction of this, parallel ray will pass through the focal point, and what shall we put? I think a convenient one would be the one that reflects off the center at equal angles. So I've chosen the rays that make life easy for me. So I have, this would be, I think, ray 3, and this would be type 1, and this is type 3. What you have here is an image formed over here. Wait now, no, that isn't even true. No, they're diverging, sorry. See, this light is coming from here. If you're looking over here, if your eye is over here, what you see is coming through the what you should see. No, see, I drew this wrong. Sorry, folks. Yeah, that's why this is interesting. It doesn't follow your usual way of thinking of things. Try to think of it this way. There's a ray that passes through the focal point through the arrow and goes parallel. So this is a type 2 ray. That one is not so easy. I could probably do that one too. But this one is a type 2 ray, which is passing through the focal point and is going parallel. Now, your eye over here, if I drew it bigger, would intercept these rays and say they're coming from over here. So what you created by this is a virtual image, upright and enlarged. That is when, this particular case, when you put the object inside the focal length of your mirror. A special case. Now that should be familiar. To the ladies, this is known as a cosmetics mirror. You look in the mirror and you see your face upright and enlarged. And so you look for all the mascara, where it's wrong, because you want it enlarged. And for guys, it's a shaving mirror. Because you look in the mirror and you see your face enlarged and upright, which is good. Whereas these other images turned out to be inverted. In other words, if you got an image of that, your face would be upside down. And you're going to see an example of that here on your way out. I'd like you to take a look at this little demo, wherein we use a mirror and get an inversion of the object. But in the case of a mirror where you get closer than the focal length of the mirror, you will get an upright and enlarged image of yourself. That's your cosmetics mirror. So that's one is probably the most familiar. The other one is a simple plain mirror where you see yourself not magnified. You see just what you are, same size, and equally distant behind the mirror. In that case, what's happening is that the focal length is infinite. And so what you get is that if that is infinite, f is infinite, this is 0, you get that the image is the same distance behind the mirror, and s prime is equal to s, so they're equal distance, they're equal height, they're upright, and you see yourself standing upright and not magnified. Wow, we have to get now. A similar story occurs with lenses. So here are the three types. The first one, well, on top there's a plane mirror. What I just said was that in that case, the focal length because the radius is infinite of a plane. The radius is infinite, and if the focal length is half the radius, half of infinite is still infinite. So the focal length is infinite, and so the formula says that the object and image distances are equal but opposite, actually, because you'll get 1 over s plus 1 over s prime is equal to 0, and so s is equal to minus s prime, which says that the image is behind the mirror, because if you see a minus, it is not in the standard form. The image is not on the same side as you. So by seeing that this is s minus, there's a minus sign, it means that the image is over here. And also, from the magnification formula, minus s prime over s, because this s prime is negative, and you have a minus sign in front, you get that the magnification is 1 plus 1. So the magnification is just, you see the same size as you are in the case of the plane mirror. But the concave mirror, you have various situations. They shown in here is what I just talked about, is the shaving mirror or the cosmetic mirror, where the object is inside the focal point, and you see this virtual image. The light seems to be coming from behind the mirror and enlarged and upright. Now, for the convex mirror is the kind of mirror that diverges the light, and it always looks like the light is coming from behind the mirror. And this is the side view mirror of your car, or the side of your car. If you see a reflection off the body of your car, do you ever see your own image? It's upright, right? I mean, when you see that image, check it sometime. Because it's a convex surface. Any convex surface will do that. And you'll see yourself walking to the car, and you'll look like you're standing upright, right? You're not upside down. So that's another convex surface that we run into all the time. And we use these special rays or the formula to get the answer. Now, I will point out just one minor little glitch here in the text. Sorry, where did I go? Yeah, there's a slight error. You see, this drawing that I have the arrow toward, it violates my rule that the taller you are, the further away you are. The drawing is wrong. That image inside the mirror, because it's taller, it should be further away. Pardon me? It's in figure 31.6c. You see the top one on the right? You see how that the image arrow is closer to the mirror than the object arrow? That can't be. If the image is taller, that means that S prime is bigger than S. S prime should be larger. So it's just blame the artist. The physicists are never wrong, right? Oh, we are, believe me. At least I am. So that's okay. And we have plane mirrors. Okay, you pretty well understand now virtual images. That is, that the image is such that it's coming from a certain place, but there actually is no light there. It just appears to be. And what's happening is your eye is correcting for that. It's collecting the light and focusing it on your retina, even though it's diverging from someplace. And we did the phantom thing to show you how you can be fooled by virtual images. And mirrors, okay. These sign conventions for mirrors, again, I would collapse them into saying if it's in the standard form, like the top one on the right, that they're all plus. If it's anything different, or any of these other things, they'll be negative. So there are your applications, cosmetic mirrors, and so on. Now let's go to lenses. Again, the story is very similar, the same formulas. Problem is that, so we have actually three kinds, just like we had diverging, converging mirrors, convex, concave, we call them. Here you have a converging lens where it's thicker in the middle, Or you have the diverging lens where it's thinner in the middle and it'll diverge the light. And if the ray passes through the center, it's more or less plane and it goes straight through. So those give you your special rays. Now the question is, how do you find the focal length of this kind of shape? And this is the formula. It's derived in the book. It's just the law of refraction. And so what appears in it is the index of refraction, n, which you'd expect, and the radii. Now, there are certain conventions on how you define the radii. So that's to make the formula work. And the idea is if you have a lens, the first radius that you have is part of a circle, R1, and if it's convex toward you, if here is where you're judging from, if it's convex toward you, we call it plus. Vex. It's called plus, R1. If it's, on the other hand, this one is concave toward you. So we'll call that negative. R1, R2 is concave, and we'll call that negative. That's the general rule. So in a case like this, we would have the formula 1 over R1 minus 1 over R2. What happens is that R1 is positive in this case. Now R2 is negative in this case, but there's a minus sign here. So you end up with, you're going to get 1 over R1 plus 1 over R2. And when you actually put the numbers in. So it just works out that you just follow this rule. For the case, for example, of the diverging lens, you come from this side and you reach this surface first. Well, it's a concave surface. It's a concave surface. R1 is concave. So it's the opposite of this convex, so it would be minus. And if you reach this surface, its radius is this one, R2. But now it's concave. Instead of being, this is now convex to you, as seen from over here. And so it also is minus. So your rule will be you'll have a R1 1 over R2. This will, oh no, it's minus. No, it's convex. This will be plus. Sorry, that would be plus because it's not concave, so it's plus. So you'll have a negative number here minus another negative number here, or a positive number here, and the overall thing where you'll have two negative numbers, they will make a stronger negative lens. And it even works for funny-looking lenses like you could have a sort of a moon-shaped lens, quarter moon-shaped lens, like that. And it'll turn out that, you see, this is going to be a converging lens because we say it's thicker in the middle, so you expect it to be converging. The point is that this radius, R1, is less than the radius of, as seen, see, this lens here has R2, but that radius is larger. That radius is larger. So the larger, as the rule is, the smaller the radius, the stronger the focusing. So the smaller radius will dominate. You can put this in the formula and you'll see. So the smaller radius will win. So you could even have things like this. No, I don't want to do that. I want to do, I don't know. No, I want to make it thinner in the middle. So something like that. Yeah. But the point simply is that the stronger radius wins. The smaller radius dominates the story. And I wanted to illustrate that by going over to explaining the eye. We said we do eye fold today, and I really want to do that. So here's a lens maker formula. In my notes, I sort of give you the, and the book, of course, does it as well, how you put signs on these things. And it's a little tricky, but not bad. So you have all these special rays. In the case of the lens, the special rays are the ones that go parallel and through the focus. In this case, it's going to have a virtual focus over here. Wow. And you can get the image by that, or a ray from here will go through the center pretty much straight, and so you'll get an image over here, say. And it'll be negative. This will be a negative distance because it's on the wrong side of the lens. This is your S prime. And it'll be negative because it's not on the other side. It's not the standard form. So those things are I think it's a little slugging through, but you can get it. And so, okay, now I want to show you a couple of little demos, but I really want to do the eye as quickly as I can. Yeah, 5 minutes. Well, here's the thing. The eye, incredible instrument. The idea is that you're going to get light, like the light that you're seeing me. The light from me is diverging. That's not good enough because you have to get, from every point on me, you have to get a beam of that light, and it has to focus down onto the retina of your eye at a certain place, which reproduces the spot that you're looking at. We did this last time, I think. Namely, that you're getting an image point for point for, let's say, here I am. And you're looking at this point. The light is coming out of there in every way because of reflection. And here's your eye, and you're going to catch a few rays through the pupil of your eye. And you're going to have to catch those few rays, and they're going to be focused onto a point on your retina, which will say that's my forehead here, or my chin would be a few rays from there are going to enter your eye, and we're going to form an image here of my chin over here. So I get an upside-down image like that on your retina. So there has to be focusing here. And I really have to show you that at first the round transparent material of the cornea acts as a lens. That's sort of like a converging lens. But in addition, the marvel is this adjustable lens here. This is the one I really want to talk about. And that is what's called a lens in this picture. And where's my arrow? Do you see up here the ciliary muscle on the very top, and it's pointing to a structure on the picture? I don't know why I don't have. What am I doing? I've got something that I didn't want. Huh? Let me see. Oh, it's a pen. Can I get just a simple pen that won't write? I don't want a pen, I want an arrow. Let's see if I have an arrow. Yeah, okay, I have an arrow. Yeah, this ciliary, that's the thing that I think is amazing. So here is your lens. It's kind of a semi-fluid, sort of a gelatinous thing. It's semi-fluid. Actually, it's made up of many layers, like an onion. But when you're young, it's movable. It actually is flexible. When you get old, like I am, it tends to harden up, and you lose the ability for it to change its shape. Because what happens is that, here we go. In the normal state, this muscle is relaxed when you're focusing at a distance. And what happens is that it tightens up on these ciliary fibers. I don't know what they call them, zonules. Okay, let me try to just draw it. What's going on here is that you have the ciliary muscle, and it's got these fibers holding on to the lens. And the fibers are fairly taut. When the muscle is relaxed, when your eye is relaxed, you're looking at a distance. You see, our eyes somehow we're hunters, so the eye is supposed to see far away. But when you want to focus the eye, let's say an object comes closer to you, you want to make the eye more round. So what you have to do is release these fibers. And the way they do that is then your muscle flexes. Now I have to show this, people are leaving. I practice all winter for this. You see, when your muscle is relaxed, it's like this. But when it tightens, it gets bigger. So it gets bigger, and therefore the little hairs relax. And this muscle and the lens can go like this. Because otherwise, when it's relaxed, it's pulled. And when you tighten your muscle, that gets long. The muscle gets bigger, the hairs get shorter, the lens bulges out, gets more round, and you focus more. So you can see an object closer to you because the lens is rounder. Isn't that a great invention? I mean, can you believe how something like that came about? That is amazing. What an engineering thing. I would have thought of that. Because you see, the lens can't move. So in order to see things closer or further, it has to change its shape. And it does that by being stretched by those things in the relaxed state. And when the muscle clenches, that thing gets bigger, and the hairs get shorter, and the lens bulges out. I think that's just fantastic piece of work. The ciliary muscle and the ciliary hairs. And this is your adjustable lens. I'm afraid I have no more time, but we'll continue, I think, on Friday. And do so. Oh, if some of you can stay, this is a very fun demo. If you go over there's an arrow on the floor there, you'll see in this mirror flowers. If you have time.